When upgrading to a 400 amp service and transitioning to an underground feed, proper grounding is crucial for safety and code compliance. Let's discuss the grounding electrode conductor, or GEC, routing, plastic water pipe connections, and well casing connections. Firstly, regarding the grounding electrode conductor routing, the GEC should be connected to the water pipe as close as practicable to where it enters the building. Practicable means that the connection should be made in a way that is both effective and feasible considering the physical layout and accessibility of the water pipe. The GEC can then be routed to the panel in the basement without returning to the meter base. This means you don't need to run a separate GEC all the way back to the meter base from the water pipe. You can connect the GEC to the water pipe near its entry point and then run it directly to the grounding bus in the basement panel. Secondly, concerning plastic water pipe connections, while copper water pipes are traditionally preferred for grounding connections due to their conductivity, plastic pipes introduce a different scenario. Since plastic is a non-conductive material, you cannot directly ground to it. The grounding must occur on a metallic portion of the water piping system. The GEC should be connected to the copper portion of the water pipe as soon as possible after it enters the basement. This ensures that the grounding connection is made to a conductive material that can effectively carry fault currents. It's crucial to ensure the connection is mechanically sound and electrically conductive, using appropriate clamps and connectors designed for grounding purposes. The connection point should be accessible for inspection and maintenance. Thirdly, the well casing connection is an important part of a comprehensive grounding system, especially in rural settings where wells are common. The well casing should also be connected to the grounding system. A separate GEC can be run from the well casing to the main grounding electrode at the meter base. This ensures that the well casing, which is often a large metal object in contact with the earth, is properly grounded and can help dissipate fault currents. This separate GEC provides an additional path to ground, enhancing the overall effectiveness of the grounding system. Ensure that the GEC used for the well casing is appropriately sized for the service and is securely connected to both the well casing and the main grounding electrode. To summarize the grounding connections, here are the key steps to follow. 1. Connect a GEC to the water pipe as close as possible to where it enters the basement. This connection should be made to a metallic portion of the pipe, ideally copper, and should be secure and accessible. 2. Connect a separate GEC to the well casing and run it to the main grounding electrode at the meter base. This provides an additional path to ground and helps ensure the well casing is properly grounded. 3. Connect both GEC to the main grounding bus in the basement panel. This central connection point ensures that all grounding electrodes are effectively tied together, providing a robust and reliable grounding system. Remember to consult local electrical codes and regulations to ensure compliance with all applicable requirements. Proper grounding is essential for electrical safety and helps protect against electrical shock and equipment damage. Understanding these connections and following best practices will ensure a safe and effective electrical system upgrade. The grounding electrode conductor, or GEC, serves as the critical link between the electrical system and the earth, providing a low impedance path for fault currents to return to the source. This connection is essential for the proper operation of overcurrent protection devices, such as circuit breakers and fuses, which interrupt the flow of electricity in the event of a fault, preventing electrical shock and minimizing equipment damage. The size of the GEC is determined by the size of the service entrance conductors, as specified in the National Electrical Code, or NEC. Table 250.66 in the NEC provides guidance on the minimum size of the GEC based on the size of the service entrance conductors. It is crucial to select the correct size GEC to ensure it can safely carry fault currents without overheating or becoming damaged. The material of the GEC is typically copper or aluminum, with copper being the more common choice due to its superior conductivity and resistance to corrosion. The GEC must be installed in a manner that provides a continuous and permanent connection to the grounding electrode. This means that the connections must be mechanically secure and electrically conductive, using appropriate connectors and clamps listed for grounding purposes. The GEC should be protected from physical damage, and any splices or joints must be made using approved methods. When connecting the GC to a metal water pipe, it is important to ensure that the connection is made on the street side of any water meter or insulating fittings. This is because the water meter or insulating fittings may interrupt the continuity of the water pipe, preventing it from serving as an effective grounding electrode. The connection should be made as close as practicable to the point where the water pipe enters the building, typically within 5 feet, and should be accessible for inspection and maintenance. If the water pipe is made of plastic, it cannot be used as a grounding electrode. In this case, an alternative grounding electrode, such as a ground rod or ground ring, must be used. The NEC specifies the requirements for these alternative grounding electrodes, including the minimum length and diameter of ground rods and the minimum size and burial depth of ground rings. Ground rods must be driven into the earth to a depth of at least 8 feet and must be spaced at least 6 feet apart. A ground ring must be buried at a depth of at least 30 inches and must encircle the building or structure. In addition to the water pipe and ground rods, other types of grounding electrodes may be used, such as metal building frames, concrete encased electrodes, and other effectively grounded metal structures. The NEC provides detailed requirements for each type of grounding electrode, including the minimum size and installation requirements. It is important to carefully review these requirements to ensure that the grounding electrode is properly installed and will provide an effective path to ground. The grounding electrode system must be connected to the main grounding bus in the service panel. This bus serves as the central connection point for all grounding conductors, including the GC equipment grounding conductors and bonding jumpers. The grounding bus must be securely connected to the metal enclosure of the service panel, providing a continuous and permanent connection to ground. Equipment grounding conductors, or EGs, are used to ground non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and appliances. These conductors provide a low impedance path for fault currents to return to the source, helping to trip over current protection devices and prevent electrical shock. The size of the EGC is determined by the size of the circuit conductors, as specified in NEC Table 250.122. It is crucial to select the correct size EGC to ensure it can safely carry fault currents without overheating or becoming damaged. Bonding jumpers are used to connect metal parts of the electrical system together, ensuring that they are all at the same electrical potential. This helps to minimize the risk of electrical shock and prevents the buildup of static electricity. Bonding jumpers are required to be installed in a variety of locations, such as around knockouts in metal enclosures, between sections of metal raceways, and between metal water pipes and electrical equipment. The size of the bonding jumper is determined by the size of the circuit conductors, as specified in the NEC. In addition to the grounding electrode system and the equipment grounding system, surge protection devices, or SPDs, are often installed to protect electrical equipment from voltage surges caused by lightning, utility switching, and other transient events. SPD are designed to divert surge currents to ground, preventing them from damaging sensitive electronic equipment. SPD are typically installed at the service entrance and at branch panel locations. The selection and installation of SPD should be done in accordance with the manufacturer's instructions and the requirements of the NEC. Ground fault circuit interrupters, or GFCIs, are another important safety device used to protect against electrical shock. GFCIs are designed to detect small imbalances in the current flowing through a circuit and to quickly interrupt the power supply if a ground fault is detected. GFCIs are required to be installed in a variety of locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electrical shock. The NEC specifies the requirements for GFCI protection in these locations. Arc fault circuit interrupters, or FSIs, are designed to protect against fires caused by arcing faults in electrical wiring. FSIs are able to detect the unique characteristics of arcing faults and to quickly interrupt the power supply, preventing the arc from igniting nearby combustible materials. FSIs are required to be installed in bedrooms and other living areas in dwelling units. The NEC specifies the requirements for FSI protection in these locations. Proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC and using best practices for grounding and bonding, you can help to ensure that your electrical system is safe and reliable. Always consult with a qualified electrician when performing electrical work to ensure that it is done safely and in accordance with all applicable codes and regulations. Regular inspections and maintenance of the grounding system are also important to ensure that it remains effective over time. Check for loose connections, corrosion, and damage to grounding conductors and electrodes. Replace any damaged or deteriorated components to maintain the integrity of the grounding system. When upgrading an electrical service, it is important to ensure that the grounding system is also upgraded to meet the increased capacity of the service. This may involve installing larger grounding conductors, additional grounding electrodes, and other improvements to the grounding system. The grounding system should be designed and installed by a qualified electrician to ensure that it meets all applicable codes and regulations. In addition to the technical aspects of grounding and bonding, it is also important to educate yourself and others about the importance of electrical safety. Teach children and adults about the dangers of electricity and how to avoid electrical hazards. Install safety devices such as GFCIs and OFSIs to protect against electrical shock and fires. By taking these steps, you can help to create a safe and electrically sound environment for yourself and your family. Remember, electricity is a powerful force that must be treated with respect. Always follow safety precautions and consult with a qualified electrician when performing electrical work. By doing so, you can help to prevent electrical accidents and ensure the safety of yourself and others. Keep in mind that this information is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician to ensure that your electrical system is safe and in compliance with all applicable codes and regulations. Stay safe and be electrically responsible.